Hi again, this is going to be module number 2. Recall that in module number 1 we looked at some rationale motivation for data science, and now we're going to have a comprehensive example, brief but comprehensive. And this, the content of this example is taken from Bishop's textbook, which is described on the course webpage. You can look at section 1.1. So this is going to be polynomial curve fitting. We have input variables x1 through xn, and they're arranged in a column vector. Hence, I was using the transpose notation. And we're not observing x, we're observing noisy target variables t. And ideally, in the big picture, we're observing t, and we want to be able, in the future, to be able to predict target variables from the input. So T are actually going to be noisy observations of x observed through some function. So we have x of n, we run it through a sine function, sine of 2 pi x of n, and we add noise zn. And again, overall, given x of n, it goes through some function, we have noise, we're observing tn, and zn is measurement noise, which can be assumed to be uncorrelated to xn. What we'd like to do, we'd like to perform polynomial curve fitting, and given observations of tn and xn, we'll try to understand, we'll try to learn the relationship between t and x, and in particular, we're going to find an order m polynomial that best explains t. So let's move to the next slide. And for some, there we are. So why polynomial curve fitting? There could be other types of curve fitting. So why might a polynomial approximations of the unknown function work? The rationale here, going back to your undergrad days, is Taylor series. Taylor series inform us that we can approximate a function with a polynomial. This could be a second order polynomial or a first order polynomial. There are different orders of polynomials that can be used. And because our function is actually a sinusoid, in this case, maybe a Fourier expansion is better in quotation marks, meaning that what we actually mean is that there would be a single term that would capture this function, explain this function well. And indeed, that's the case here. But oftentimes we don't know that we're dealing with a sinusoidal function or a exponent or whatever it is. So side information about the problem can be very useful. And in this problem, the side information would be, hey, among the families of all possible functions, our function actually has a really nice Fourier expansion, but oftentimes you don't have that. So in our case, the true function is sparse in the Fourier basis. Sparse means that a small number of non-zero elements would describe the function very well. Sometimes we have this side information, sometimes not. And by the way, you may be hearing a bell ringing, and that's the famous parrot. So, okay, so we understand that we don't always know that what basis it'll be sparse in. We don't know that a Fourier representation will work well. So we're left with this Taylor series, polynomial curve fitting. And what does best explain mean? So suppose that we have polynomial weights W. That's hypothetically what we'd like to do. We want to predict t, the target, as a function of x, the locations, and the weights. So t prime, our prediction is going to be w0, a constant, an offset, plus w1 times x, plus w2 times x squared, up to wm times x to the power of m. So the w's are weights. And another way to think about it might be, you might have a vector of w's. So w would be w0, w1, up to w capital M. And you'll note that this vector is of length capital M plus 1. And you'll have a second vector. Let's call this x tilde. X tilde would be powers of x to the power of 0, which is 1, x to the power of 1, which is x, x squared up to x to the power of m, and y as a function of x and w is going to be w multiplied by the transpose of x tilde. Now recall that in linear algebra, w is a row vector. X is also a row vector, but when we transpose it, and I'll highlight the transpose with this different color, when we transpose it, we have the row vector for W is multiplied by a column vector for X tilde transpose, and a row multiplied by a column is called an inner product. We take the products of corresponding pairs in the two vectors, and we add up all the products. Okay, so that's a simple way in linear algebra of denoting what's going on. And we don't know what the optimal W's are. So we want good W's, and we're going to provide a score for the W's. E of W will be a summation over the squared error between y as a function of x and w and the true target observation Tn. So y of x and w minus Tn, we're taking that in braces, we're squaring it, and we're summing over all the indices from 1 up to capital N, and we have capital N observations of x's and t's. So what we'd like is the w that minimizes E of w. I asked what does best explain means. In our world, we'd like a low squared error E of w. You could have a different score for different scenarios. Now, why squared error? So we're summing over the squared error between y and t. Y is the predicted function, the curve fit function from x with weights w, and t is the observed target function. And there are different types of error. We could have used absolute error, and that might emphasize what I would call typical errors. And the mean squared, or the squared error, it puts more emphasis on the larger errors because we square them. But the absolute error puts less emphasis on the larger ones, and it puts more emphasis on the typical or even small ones. And if you want to put more emphasis on the outliers, if you want to have very few outliers, you could use even a higher power than 2, like, for example, a power of 6. And you could have an error metric, and the error metric could coincide to a statistical distribution of possible noise. So recall here, when I'm saying possible noise, recall that T is equal to f of x plus z, and this is t at index n, x at index n, z at index n. And now, if z is Gaussian, then the overall error among all the samples, all the target variables, the probability of the error is going to be proportional to, for each of the individual zn's, an exponent of negative zn times, or negative zn squared times some constant. And when we look at the probabilities of multiple zn's, we're multiplying probabilities, which really means that, and I'll try to type here, so an individual Zn has probability density constant number 1 times exponent of minus the square of Zn, and we have inside the exponent constant number 2. And I'll just try to add myself more space. And then when we have a vector of z's, and the vector is of length n, we have c1 multiplied by c1 multiplied by c1 n times, so c1 to the power of n, multiplied by the exponent of minus c2 times, in parentheses, z1 square plus z2 square plus all the way to zn square. And this inside the square brackets, this expression z1 squared plus z2 squared plus all the way up to zn squared is the squared Euclidean norm of, if you think about it, the squared length of the vector z. And the error metric could reflect that. So if it's Gaussian, the squared error makes sense. If there's another type of noise, if the noise doesn't have a Gaussian density, as I wrote on the top line of this text box, but a different type of density, there may be a different type of reasonable error metric. Okay, but this is just a comment, and we're going to be revisiting this type of idea over the next few weeks. So the math analysis, and again, we're going to be revisiting the details later in the course. We could write that y as a function of the first location, x1 and the weights, up to y as a function of the last location, xn and the weights. This is a column vector, and we can express this as a product of the powers of x1. x1 to the 0 is 1, x1 to the 1 is x1, up to x1 to the power of m. That's in row number 1, x1, powers of x1, multiplied by the weights, w0 up to wm, in the column vector to the right of the matrix. In row number 2, we have powers of x2, powers from 0 up to m, so 1, x2, x2 squared up to x2 to the power of m. And finally, in the last row, we have powers of xn. So in general, this matrix has n rows, and it has m plus 1 columns. And in shorthand, we can write that this entire matrix, we can denote it as capital X. And this vector can be denoted by lowercase w. Typically, we'll often use capitals for matrices. Y as a function of x and w is the matrix X multiplied by the vector w, matrix vector product. Recall that the truth t is sine of 2 pi xn plus zn. We're going to search for a vector that minimizes the squared L2 norm between y and t. Y are the hypothetical explanations using the weights w, t are the actual observations. I was saying here Euclidean norm. So recall that an LP norm, which is denoted by these double brackets around z subscript p, that LP norm is a summation over all the elements of z to the power of p. And after taking this summation, we take the summation, the entire summation, to the power of 1 over p. Similarly, if p is equal to 2, then the Euclidean norm is a summation over the squared values. And after taking this summation, we take things to the power of 1 divided by 2, or half. Powers of half are square roots. So we have square root of summation over n zn squared. And if we ignore the square root, what's inside the square root is the squared Euclidean norm, which is often denoted by, again, this double square bracket, superscript 2. And we often implicitly assume subscript 2. That's the standard norm, the 2 norm. We're going to study later in the course in a few weeks the least squares technique, and it finds the w that minimizes this squared Euclidean norm between x, w, and t. And in closed form, the optimal w denoted by w star is x transpose multiplied by x. All of that we invert it, multiplied by x transpose times t. This entire matrix, which I'll now do I'll go back to the red color, is denoted by x superscript plus. Okay, again, we're going to study this later, but in the meanwhile, this is a closed form solution for the optimal weights vector w. So now let's check it out. There's MATLAB on the course webpage. There are conversions to Python of everything on the course webpage too, so you can go and experiment at home, and let's look at several examples. We have data, we have n equals 10 noisy observations, and we begin with a 0-order polynomial, which basically means a line, a constant. So in the horizontal axis here, we have the input, the xn. The vertical axis are going to be in red, the observations, and the red circles are noisy observations. And the truth, the black curve without the Zn, is the black sinusoid. And the 0th order term, the polynomial, would be basically some constant, which happens to minimize the squared error between that constant and the vertical levels of all these data points. And again, the vertical axis is the t's, the horizontal axis is the x's. So clearly, a constant doesn't approximate a polynomial well, because every single t, we're going to be approximating it by the same y. So maybe a higher order, maybe a 3rd order. And now we have the same red dots, red circles as before, the same black truth, the sinusoid. And our polynomial fit of order 3 is starting to look kind of a bit like the sinusoid. Not exactly, but acceptable. So maybe higher order, maybe order 20. So order 20 with 10 points, n equals 10, that doesn't make sense. So what'll happen in that case is that if the order of the model is larger than the number of points, you'll get a perfect fit, but that's meaningless. But now suppose that we have 50 noisy observations. Well, an order 20 thing will still lead to overfitting. So here we see that the polynomial fit, the blue line, goes up and down like crazy, although we have quite a few 50 observations. So maybe we want to use a higher order, but not too high. So let's see. So what about if we use tons of observations? So 1,000 noisy observations, going back to the 3rd order fit. Now the blue and the black black is the truth, the blue is the polynomial fit. The black and the blue are pretty good. And if you would do a 5th order term, a 5th order Taylor approximation to a sinusoid is probably pretty good. So here's a discussion. When you have more observations, you have a better curve fit. That makes sense, assuming that the model order is fixed. If m is too small, small model order, for example, the constant, or even a linear, just like a line, it would probably be a bad fit for most functions. A large m is probably going to create overfitting. That's the case that I showed that the polynomial was going crazy. So the challenge is, how do we estimate a good model order? A possible solution is test data. You'll partition your data into 2 parts. Most of your data, or part of the data, will be training data, which you'll be using for calculating the optimal weights, the W's, and you'll hold back part of your data as test data. And after training, you're going to evaluate how well that W explains the test data. And after running this several times, you're going to be able to have a curve. So in your curve, the horizontal axis will be the model order capital M, and the vertical axis will be the error. And typically what happens on the training data, when M becomes large, a high model order, you get really low errors on the training data. So I'll just jot down here in text that this would be training. But now, what about the test data? So the test data, what typically is going to happen is that for small model orders, again, it's a constant, it's a line, it's terrible. So initially you have a lot of noise and it starts going down. And at some point, it starts overfitting. Now, what I'd like you to observe, so again, this is test error. What I'd like you to observe is that typically the test error per element will be larger than the training error, because the training, we basically optimized the parameters to be great for the training data. Now test error, it'll likely be a bit larger. And for small order terms, the testing error will be only somewhat larger than training. But for higher order models, the test error will go, again, it'll go crazy. So the sweet spot will be the sweet spot will be, and for some reason it doesn't want me to draw, in this area. In this area, you can see that the test area is reasonable. Now, there are other ways to do this. We'll discuss these other ways, but this was merely a quick example of how polynomial curve fitting, how it works as a technique for learning functions. So that's it for the second module, and we'll continue next time.